So we'll continue our discussion here of the energy transport in the simple way that we have been looking at. If, as I said before, if you go to the chapter in Holton, you will get actual eddy transport calculations with the heat sources and so on and so forth. At the end of this chapter, I'll briefly introduce the approach of Holton with some figures. Okay, so to kind of re-emphasize the point I made in the previous podcast about the northward transport by Hadley cells, you can see that the divergence away from the deep tropics is shifted away because the ITCZ is asymmetric and the Hadley cell is also asymmetric because of the maybe because of the differences in hemispheric land distribution, or because of the transport by the ocean, which we will not get into at this point. But the main point is to see that the transport away from the deep tropics in the Hadley cell is quite low in low latitudes within the Hadley cell, but the transport by the ocean here, the thin solid line here, is almost done by the ocean. The total transport is this solid or bold black line. So you can see that the ocean is accomplishing most of the transport at low latitudes, whereas when you go to high latitudes, the ocean's role almost disappears. So the ocean transport is all done at low latitudes, whereas at high latitudes, it's the atmosphere that's doing all the energy transport required to balance the energy gain and energy deficit in the low latitudes and high latitudes respectively, right? Looking at the energy transport then at mid latitudes, you can write it as a longitudinal azimuthal distribution, 2 pi a Cp over g cosine phi. So this is again the distance from the rotation axis to the atmosphere at that particular latitude, and we have the integration terms from the surface to the top times the meridional velocity times the average temperature at that point. Okay, I'm kind of showing the simple expression from the book because we have not gone through the derivation itself, and we will not. We will just make the points about the eddy transport and leave it at that. So this number, if you plug in the appropriate scales and values for the expression, turns out to be about 8 petawatts, which is consistent with what we need here in terms of the longitudinally average northward transport in both hemispheres. You can see there is quite a bit of an symmetry in both hemispheres because we have averaged over the whole longitudes, and the zonal asymmetry goes away. So taking values of the radius of the Earth at 6371 kilometers, value of Cp, heat capacity at constant pressure, G, the average surface pressure, a typical meridional velocity of 10 meter per second, and typical atmospheric temperature at about 45 degree latitude in either hemisphere of about 3K. Okay, this is averaged deviation from the annual mean. You will get mid-latitude northward heat transport of 8 petawatts. This is what the eddies have to accomplish. Okay, we have seen all these wiggles in the eddies, and we plug these numbers into this equation and we end up with about 8 petawatts. So we have looked at this before as momentum transport, where we said the trade winds in the low latitudes are picking up westerly momentum. There is a trade inversion here. Maybe I'll show a figure of that again in the next podcast. and deep convection here lifting the energy to the upper atmosphere, and the angular momentum as well, and the angular momentum is getting transported poleward. And I have said already that the termination of the Hadley cell is not completely understood. The argument could be that this is where the baroclinic instability starts in terms of the angular momentum breaking down, but the subtropical jet stream that exists here is not exactly at the termination of the Hadley cell. There are all kinds of details which we have skipped in this introductory course because many of them cannot be done without going through the equations. So, poleward transport of westerly angular momentum by mid-latitude eddies shifts these westerly cores poleward. So they are not at the termination of the Hadley cell, but they are much poleward of the termination of the Hadley cell. Looking again, the net transport of angular momentum out of the low latitudes, and momentum supply is needed for balancing generated by the surface friction. So we had the energy transport. Even though we are saying Hadley cell here, we know that in reality it's the ocean and the atmosphere together that are moving the energy poleward, and beyond the subtropics, ocean basically has very little role to play, and it's all by the atmosphere, which means all by the eddies. Okay, so the atmosphere is very energetic in the mid latitudes, storm tracks and so on, which we will not look at much, but Holton has a very good chapter on that, and that's what does most of the energy transport beyond the Hadley cell. Momentum transport, Hadley circulation again, and beyond the subtropics you get again momentum transport by eddies. There are details here. Just because the heat transport, energy transport is constrained to be northward, doesn't mean eddy momentum transport is also northward. It turns out that angular momentum is not conserved. We already know that the baroclinic instabilities result from that. So there is this angular momentum transport that is very different than the heat transport, because there is no constraint on the momentum transport other than that the net torque of the westerlies and the easterlies has to balance, and Earth cannot keep wobbling too much. Okay, there's a slight wobbling which shows up as change in the length of day, and that's about it. So the momentum transport, if we look in a simple argument here, if you had just a circular eddy, look at it in the meridional zonal plane. So you have y is going poleward with meridional velocity v, and x is going in the azimuthal or zonal direction on the sphere with velocity v. If you had just a circular eddy, then u is positive here, v is positive here, so average momentum being carried is positive, is net is positive. Same amount of negative momentum would come in. So across this latitude line, you would basically get no net transport, and the same thing happens here. V is positive, U is negative, and here V is negative, U is positive. So you will end up making no net northward transport of momentum. That's not good. We need net northward transport to create the westerlies which have to balance the torque, right? So you end up with this banana shaped eddies, which is kind of related to what we were saying before about how the warm air and the cold air have to move energy as well. Okay, so here you have U positive, V positive, and here you have V negative and U negative. So you end up with U V average being positive, and here U is negative, V is positive. Here U is positive, V is negative. So you end up with negative UV bar. Okay, so this means the weather systems can actually have a net transport of momentum across this latitude line if the eddies are actually, or the momentum transport by the eddies is in this kind of banana shape. This is a very simple heuristic argument, but I think it's a very strong argument. It's very intuitive as well. Okay, and that shows up in most of the quantities we would look at from satellites, as we'll see in a minute. So westerly momentum must be dissipated in mid-latitudes, and surface friction acting on the westerlies is going to do that. So the upper atmosphere has more steady flow, as we already saw once, and we will see again, whereas the surface breaks into these eddies because of this interaction of the westerlies with the surface. So here are our banana-shaped eddies, or the transports happening along these angular features that we see from southwest to northeast, and southwest to or northwest to southeast in both hemispheres. So the equator is down here. Okay, here is all the continents you can see. So these features that we saw in the satellite before is directly related to this requirement that there has to be a net transport of momentum and energy across latitude lines. Okay, so you can see that this also shows up in this cloud top various quantities observed from satellites. Okay, these are synoptic observations of cloud tops, ice, sea surface, and so on and so forth. Okay, it's beautiful, right? The theory really works. So we are not just kidding about the requirement for eddies to transport requiring certain shape. Okay, so just intuitively develop a sense. If you're doing tropical climate, tropical meteorology, you're not going to deal with much of this because you will go into El Nino and monsoon and other things which are somewhat more linear than this eddy dynamics in the mid-latitudes, and waves become much more important in the tropical climate, whereas the eddies and waves become very important at mid-latitudes. So that's a very general statement, but if you get into deeper research in either regions, you will see what I mean.